Hello, everybody. Welcome back to our webinar. This is the second episode in which we will be talking about PVD technologies, and we will tackle some aspects related to them. In the first episode of our webinar, we have previously spoken about the opportunity to apply Optitune's nanocoatings to PVD manufacture as well. So let's first dive into PVD technologies, and in general, on the market, two main PVD technologies are available: evaporation and sputtering. When it comes down to evaporation, an electromagnetic field is usually applied on the surface of the metal target. This will cause evaporation of ions, which are, of course, charged particles. This will travel in the PVD chamber, where some gases have been previously ejected, and collisions between ions and gases will result in a plasma cloud, which eventually will condense on the substrates and give rise to PVD coatings themselves. Some cases in point of evaporation technologies are the cathodic arc evaporation, but also thermal evaporation and electron beam PVD. On the other hand, we have sputtering, in which the extraction of metal particles is different. It's not by means of an electromagnetic field, but it's a mechanical extraction. A gas flux is directed on the surface of the metal source itself. This will extract some ions, which will be traveling in the PVD chamber and will collide with gas particles in order to give rise to a plasma cloud, which will eventually condense on pieces to generate PVD coatings. Two important examples of sputtering technologies are magnetron sputtering and high PMS as well. One, in this case, may wonder which one of these two technologies is better. So we have pros and cons. When working with evaporation, the deposition rate is higher, which translates into a higher productive output in general. And this would mean that, on the other hand, we cannot really easily control the film growth or the film defects density. And the range of metals that can be evaporated is not really wide, because evaporation is strictly dependent on the trend and on the relationship between the vapor pressure and the temperature itself. On the other hand, sputtering may be lower in terms of productive times, lead times. As a matter of fact, the deposition rate here is generally slower, but this comes with other advantages, like, for example, a better film growth, and also a much lower film defects density. And the range of metals that can be used here is actually broader than the case of evaporation itself. So which technology is better? There is no clear answer to which one one should choose, because it's strictly dependent on the kind of application we are pursuing. As a matter of fact, if we take a look at case one here, for example, we will be working with the external parts of aerospace shuttles, which are, of course, surfaces that must withstand important, let's say, important temperatures, important atmospheric stress, and intense solar radiation as well. So a more uniform film is much better than a porous film, which could be obtained, for example, through evaporation. So depending on the particular case, sputtering may be preferred over evaporation. Whereas here, in the second case, we see that we should apply PVD coatings to internal parts of luxury cars. Of course, this is mostly a decorative application. And this means that it doesn't really make a difference if we use either technology. Of course, we know that PVD is a really flexible technology which can be applied to different kinds of surfaces, but this, of course, would come with some requirements. For example, the level of contaminants and pollutants on surfaces should be reasonable, and these particles should be easily removable with cleaning processes at an industrial level. On the other hand, of course, we cannot work with other kinds of phenomena like oxidations and passivations, because these would change the behavior of the surface itself. So the PVD adhesion could experience some issues here. Then we should consider that the material suitability to the process is really dependent also on the kind of PVD technology we are working with. For example, some evaporation techniques usually operate at high temperatures, which is a condition that is not really feasible to work with plastics, which is really highly deformable. And other kinds of materials like glass and ceramics can be coated as well with PVD. But of course, the PVD processes here should be, let's say, properly tuned. And generally, most metal surfaces and interfaces are very good starting points to work with PVD. Well, in the case of many or let's say all PVD technologies, we have a wide set of parameters. The most elementary ones are vacuum, temperature, gas flow, and metals that are used in the process itself. For example, when speaking about the degree of vacuum, it's really important that the PVD chamber is, let's say, under high vacuum, or it is at a certain degree of vacuum, because this would determine the degree of purity of the final PVD coating, which should be good enough. Then the process temperature should be tuned properly depending on the material we're working with, but also when we increase the temperature, for example, the film adhesion can improve. And in some cases, we may have a higher hardness as well. Gas flows are important too, because depending on the quantities of gas, of course, we can determine a different color. And metals are a crucial part as well, because depending on the application, we should use a certain kind of metal, for example, when we're looking for a corrosion resistant coating, and we should avoid other ones. Let's take into account now an example of PVD coatings, basically in the decorative field, made with zirconium, carbon, and nitrogen. This kind of mixture would allow us to obtain, let's say, this range of colors here in the first picture. So colors which go from light gold to a bronze, let's say. We can see that this kind of coatings, or we can obtain with this mixture a particular coating which can be applied, for example, on stainless steel. And this can actually lead to an improvement and of an increase in terms of hardness of the surface itself. Indeed, IEC 304 is around 600 Vickers usually, but with some kind of coatings obtainable with this mixture, we can go up to 4 times. And to the first part of 10,000 Vickers, which is the hardness of the hardest element in nature, diamond. Also, we should be able, for example, to improve the salty corrosion of these materials as well by 6 or 7 times too. So we can now understand why PVD technologies are really popular and they have broken into the market. Here, for example, we can take a look at some figures taken from Grandview Research. In the left graph, we can see the predictions in terms of the PVD market at a global level. And the compound annual growth rate here is around 8%. And this indicator actually refers to the revenue increase between 2 consecutive years. And of course, we can see that most of the market is led by spatter deposition and thermal evaporation together. And arc vapor deposition represents usually the smallest part of the market. In terms of the market concentration, PVD is not a very highly concentrated market. It's characterized by a high degree of innovation. It's not frequent to see merger activities here. And the impact of regulations on this kind of market is high. And of course, it will be growing in the upcoming years because its varied and numerous applications. So the next episode, we are going to speak about Optitune's nanocoatings. So in terms of technical requirements of the materials themselves, the range of applicability, and some performance and test methods. Thank you so much for your attention and see you soon.